So we'll begin with a keynote speaker, and our keynote speaker for today will be Dr. Ripudaman Malhotra. He's an organic chemist, and during his 36-year tenure at SRI, he worked extensively on the chemistry of processing fossil fuels. In 2005, he joined Hillcrew and Ed Kidaman to co-author A Cubic Mile of Oil, The Looming Energy Crisis and Options for Averting It, which was published by the Oxford University Press in 2010. Among his technical works are over 100 papers in iCover literature. He is a section editor of Encyclopedia of Sustainable Science and Technology. In 2005, he was named an SRI Fellow. In 2015, he was awarded a Stotch Award for Fuel Sciences by the Energy and Fuel Division of the American Chemical Society. In 2008, he was named an ACS Fellow, and in 2019, he was introduced into the SRI Hall of Fame. Thank you.
Thank you, Mr. Arma, for the kind introduction. I'm really pleased to be here to attend this meeting. I was at the GOPE 2019, where I spoke about global energy situations and gave a talk about replacing the cubic miles of oil. And it may be a foreign concept at the moment about a cubic mile of oil. It'll become clear. That's my favorite unit of global energy that I talk about. Today, I was asked to speak about, give this keynote, and I was honored to be able to do this. So let me share my screen with you and my presentation. And the title that I have chosen is, the role of bioenergy, which was something that we discussed with the organizers, that I should speak on the role of bioenergy in achieving sustainability. Now, there are two keywords in this title. There's bioenergy and there is sustainability. So bioenergy has assumed various meanings for different people. And what I would like to think of is that it encompasses both the use of energy for producing electricity, as well as for the fuels. So I was looking at the program and I see that many talks today are talking about using biomass to produce electricity through gasification, combustion, and the heat processing, thermal processing of that. And then there are quite a few also on biofuels. The other word that I want to emphasize or talk about is this word sustainability. The word sustainability has the same root as sustenance. And when we talk about global energy or our society, for the modern society, sustenance takes the form of energy. We really need energy to sustain us. And it's absolutely essential for the way of our living. Take this Zoom meeting. It's made possible because we are using electricity and producing that from a variety of sources. Electricity in particular, and energy in general, is what lifts us out of poverty, gets us away from the drudgery, and allows us to pursue other aspects of life other than simply hunting and gathering. However, the bulk of the energy we use today comes from the burning of fossil fuels, with the attendant consequence of increasing the CO2 concentration in the atmosphere. And this increased CO2 impacts our climate and it threatens our existence. It's a huge problem, but it's also an equally huge opportunity. It's interesting to note that the kanji for challenge has in it also the kanji for the door. Let me see if you can see my, so this would be the kanji for the door on the outside. All of it together is what presents as challenge. As I said, the amount of energy that we have in biomass globally available is small, but nonetheless, bioenergy has an important role in addressing this dual challenge, and that's the part that I will like to talk to you about. So let me introduce this concept of a cubic mile of oil. Some of you who attended last year may be familiar with it already, or may have heard me at other times. Anyhow, think of it as it's a visualizable image that you can make in your mind about what a cubic mile of oil might look like. Now, my colleague Hugh Crane, while he was waiting in the gasoline lines back in the 1970s of the time of the first oil embargo, came to the realization at that time that the global oil consumption was approaching 1 cubic mile. So he thought of discussing all the energy flows of the world in terms of 1 cubic mile. Imagine a pool that's a mile long, a mile wide, and a mile deep, filled with oil. That's roughly 1.1 trillion gallons of oil, or 26 billion barrels of oil. In terms of SI units, that embodies 160 exajoules. In terms of BTUs, it's 153 quadrillion BTUs, or quads, as the US Department of Energy talks about. And when that amount of energy is converted into electricity, since only a part of it gets converted, 2/3 of it is almost lost, we get about 15.3 kilowatt hour of electricity. So it's a large amount of energy, but it's appropriate to use in the context of global energy flows. Otherwise, we get easily tripped over by these millions and billions and quadrillions. Other than that, we'll be using about 2, 3, 4, things like that. And by the way, this is what 1 BTU looks like, a burning match. Or about 1,000 joules. Now, the energy is important, as I mentioned. It's the way we lift people out of poverty. It's the one that gets us out of our drudgery for just eking out an existence. This is a chart that has been that I made many years ago, using data from the World Bank for the United Health Development Index that was developed. That's the composite, which uses not only the GDP, but also other parameters like accessibility to education, freedom of political freedoms and things like that. It's a composite. But it showed that countries really climb up this ladder by increasing their per capita energy consumption up to a point. After a point, you don't get any more higher on the UNHDI. Um, US, for example, on this scale is off the charts to the right. It's about 2,400. So I have plotted here on this axis here, per capita energy consumption in gallons of oil. And again, I use gallons of oil as a unit of energy, the amount that is embodied in 1 gallon of oil. It's something you can visualize, you hold in your hand, that you're familiar with it. I don't like to talk just in terms of BTUs because it gets very difficult to imagine. So allowing the world's population to lead healthy, productive lives would require us on a global scale to increase the total amount of energy that we use. And the question is, where do we get that? That's a very large amount of energy. And here's a chart that I looked at based on the British BP. It's a statistical review of global energy. They publish every year, and I've been making these charts ever since I wrote the book back in 2006. So in 2018, sorry about that, oil consumption was 1.23 cubic miles of oil. Coal was about 1, natural gas also approaching 1.87, nuclear 0.16, hydro 0.25. Other renewables, meaning wind, solar, geothermal, etc., correspond to about 0.15. Biomass energy this is a number that I did not take from the BP. BP does not provide that. Biomass energy is a little difficult one to estimate because this is not a traded commodity, so we don't get good records, but this is what people think in terms of foraged materials, wood and trees and shrubs and stuff like that that people use, or animal dung for heating and cooking. And the World Bank has provided some estimates of that. And so the 0.33 comes from there. In 2018, the total consumption of primary energy in the world was about 4 cubic miles of oil. And you can see out of this 4, more than 3 are provided by the fossil oil, coal, and gas. And that's the problem. And the question is, how do we get that much 4, or which may be required, maybe increasing to 8? So it's clear that biomass alone cannot provide it. I don't think that it has. That couple of talks later, there is a speaker who will be talking about from Bangladesh, Sarkar, will be talking about the application of nuclear. I'm pleased to hear that. I don't know that I'll have to watch his presentation maybe tomorrow morning later on a recording. Please excuse me, it'll be way past my bedtime. It's just the fact that we are getting so much of the energy from fossil is not something new. It's been going on for a fairly long time. Well, historically, before the start of the Industrial Revolution, there was the world was pretty much living on biomass and only biomass. But if you look at the last 20 plus years, oil, coal, and natural gas have really dominated the supply of energy for us, with the consequence of the climate change which we are facing. And now the question is, we want to replace, we have to increase the total supply of energy on the one hand, but also replace it with non-carbon sources. Now, bioenergy is a carbon source. The only reason it is exempted, people don't, is because carbon dioxide that we burn in the burning of the biomass has only recently been absorbed from the air. So it's being cycled. So that's why it's called somewhat of a renewable resource. Although I do not like the term renewable energy, because energy is never renewed, energy is only dissipated or changes one form to the other. Anyway, be that as it may, let's look at the total available resource of the global biomass. And the estimated production of biomass in the whole world is fairly large, 75 billion tons a year, although most of it is in the forest and in the marine. This is the marine, the algae or other phytoplankton. They are the ones that produce the oxygen for us, pretty much, and of course, also the forests. And they provide many other services for our existence. And that's not the biomass that we want to access necessarily. We want to access the biomass which is recoverable on a renewable basis on a short time cycle. And so that's the one you'll be getting from savannas or from swamps or the terrestrial. And if you look at the estimates that people provide us for the recoverable biomass resource, it's about 3 billion tons annually. Biomass has a heating value of about 15 gigajoules per ton. So the energy from 1 billion tons is 15 exajoules, which is only about tenth of a CMO. So even if you get all of this, that will be 75 billion tons will be, that is the entire world's biomass. That'll be about 7.5 CMO, which is where the world is headed for our total consumption. But then there'll be no trees, no algae, no phytoplankton, no biomass, nothing for anybody else, and no food for us either. We'll only be using it for energy. So that's not a very happy thing. So biomass can provide some energy, some useful energy could be obtained, maybe about 0.3 CMO or 0.5 CMO, may be able to push it to that level of our total need for about 6 to 8 CMO by the middle of this century. So let's see how we can, what are the various options that we have. And the options are really plenty. You have different feedstocks, we have different processing, and you can combine things in a variety of ways. For bioenergy means producing electricity, you can look at the forestry residues. By using forestry residues, you may also be able to prolong the life of the forests and minimize forest fires. Of course, there'll be other challenges with it. For this, you may be looking at particularly fast-growing trees that you could cycle on a short term, on a decade scale time frame. Then there are the crop residues. So after the grains have been harvested, what's left behind, are there ways that crop residue, is it just simply plowed under? Are there other ways of using it? Can we use that for producing electricity or biofuels or something like that? Biofuels, if you want, you've got the other two main things are the biodiesels and the ethanol. For biodiesels, people look for crops like palm, jatropha, rapeseed, or algae. And for ethanol, the two main things are the corn or the cellulosic form. These are the starchy oats or this. And then, of course, I forgot to mention sugarcane. This is the other one, the cane sugar. That's another big one in there. And then in terms of the processing, you have both microbial or enzymatic fermentations and things like that, as well as you have thermal processing. And some people will be talking about the gasification or pyrolysis. Pyrolysis to produce, taking crop residues to make biochar is an interesting idea because it deals with the crop residue. It doesn't pollute and gives you a biochar, a product that the farmer can use to improve the soil quality. So there may be benefits. It's just that these things are expensive and sometimes it's hard to implement them. But that's where creativity of people come in. And I hope that some of you are able to figure out ways of how to either build cooperatives and how a transportable pyrolysis system, biochar manufacturing can be used to save that problem. So when you're considering bioenergy, you have to look at some of the questions is, first of all, how much energy can we derive? Do remember that growing biomass is often energy intensive itself. So what we really have to look at is this parameter. It's called energy return on fossil energy invested, EROFEI. I know it's many of you may have heard of the EROI, which is energy return on investment. But I think that is always net negative because we always have to put in more energy than we ever get back. What we really want to look at is the energy, the fossil energy that we have put in, because that's where that's what we want to avoid. So for instance, the diesel that is used in the tractors or plowing the fields and transporting the lumber, etc. During the processing, coal or natural gas that is burned to distill the fuel out. These are all fossil energy investments. And you have to look at, well, for X units of fossil energy that I put in, am I getting back at least X plus Y units of energy, something net positive. And in doing so, am I also able to reduce the total carbon emissions in the atmosphere? Because that's the other main objective that we have to, that should be on our mind all the time. And that is and to measure that, the way to do that is through detailed life cycle analysis, or LCA. And if you are quite familiar with it, I'm sure. Other things to consider would be the land and water resource requirements, as well as on the positive side, maybe there are some other services such as waste management or pollution reductions that can be achieved by the use of bioenergy. And these things all get into the mix of the considerations for uh, how to proceed. So to kind of summarize a little bit, if you're looking at bioenergy crops, these are annual. Well, what happens is that even if you're going to use it just for the energy, you're using the same land that could either be used to produce food for humans or feed for the animals that can then be eaten by the humans, or something like that. So there's this competition. And then these also require fairly large amounts of water, as well as energy intensive fertilizers to keep them going. For bioenergy, another thing of consideration is the fact that the amount of energy, the volumetric energy density of bioenergy makes transportation an issue. Let's say you want to power a 100-megawatt plant. The area that you require to power that is 160 square miles of to harvest the biomass. So think about if it's 160, so how far are you willing to transport the lumber? Because that's an additional cost. If you want to look at the wastes, and even in our rather wasteful society, we see that it's still limited. The global estimate of the total waste is only about 2 billion tons, or about 0.2 CMO of biomass. So that's waste is it's still not that large. Is not enough to supply us. We cannot just conserve or our way out of the problem. We cannot just improve the efficiency and get our way out. We should certainly do that. Don't get me wrong. Waste is bad. We have to stop the waste. But if you are going to get only this much energy, 0.2 CMR of it, you have to think about, well, how much am I going to spend on that? But then on the positive side, please look at also at the societal benefits that may accrue through waste management or pollution reduction things. And I'll talk a little bit more about it in a second, just a second. Here it is. For example, open field fires, in the, this is a picture from New Delhi in the winter time when the farming over there, the fires are lit on their things because the farmers want to get back for the next crop, and they do the open field fires. And it creates a toxic smog at that for not just this picture out of the city, but it really, the whole country gets blanketed by that. It's also the change of weather. There are other factors in it. The real need is there to allow those farmers a cost-effective technology that would take the thing so they don't have to spend too much in harvest, in kind of removing the stover that's there, the remaining crop that's standing there after the harvest is over, that the residue, the crop residue, you don't want to, it's not much value in it. But the quickest way to do is to just light the fire on the field, but that leads to all this problem and health problem, and the society bears an enormous cost in terms of increased respiratory ailments, premature deaths, and things like that. So that's a benefit that could be avoided if you could use those crop residues to produce bioenergy, or if you're not going to produce bioenergy, make biochar, Maybe as a cooperative, you could have a transportable biochar furnace that can go from farm to farm and provide this service. It has to be figured out. There are lots of questions, lots of details, and I'm not giving all the answers today, nor do I have all the information to tell you. But I was pleased to see that there are places working on this, and there are many designs for these biochar furnaces, inexpensive ones that might be adaptable. So oops, I think I went the other way. So now let's look at biofuels, the other side, in the last couple of minutes that I have. Why biofuels? Well, it really started back in the 70s out of concerns from energy security during the oil embargoes. And Brazil took a big lead in terms of, at that time, said, well, we will solve the problem by growing our own fuel. We will make ethanol. We have plenty of sugarcane. We can grow that in this country. And they made a huge, they started to scale it to the point that could provide about 80% of their fuel needs using sugarcane to ethanol and all that. In the US, initially the impetus in the 70s, of course, was, well, we will use coal and make coal into the liquid oil. And that was a coal to liquids project. That was my entree into the world of energy research back in the early 80s, 1980s. That's when I started on that project. But later we moved on when we realized that the coal isn't the way we need to go. That's another fossil energy, and we have to get away to something renewables. And hopefully we could grow corn and use corn and the starch in it and ferment it into ethanol. Europe decided to proceed with the base of going to biodiesel, because there are more diesel cars in Europe also, using palm oil, rapeseed, and things like that. The other impetus was for that the oxygenates, both biodiesel and ethanol, they promote cleaner burning, both in terms of soot and NOx reductions. And the hope was that we could also reduce carbon. But what happens when you do all the analysis that I told you about, life cycle analysis, ethanol really may be able to reduce the CO2 emissions by 20%, depending on things. That's a low end, but are at best to about 50% of what you would get from burning gasoline. So it's certainly not the answer to really go for deep decarbonization, which the world needs. That, of course, will require us to use much larger investments in nuclear power, but that's not my talk for today. Now, in terms of what's driving biofuels today, of course, are the renewable fuel standards. These are the mandates, the policy mandates that are driving it. If you look at, this is the chart from a few years old when these mandates were being implemented. There's a huge growth that was being projected, and not aware, because the corn-based fuel would cap out. They recognize over here about 15 billion gallons of oil, and that's where they are. They're stuck. There was the expectation that we will have a lot of cellulosic or advanced biofuels. Those just haven't been met. They haven't materialized. And even today, it is still, the US is about 15 billion gallons. That's about 10% of the US gasoline consumption. Biofuel productivity is kind of low. The area requirements are huge. What I've shown on this chart are the different kinds of crops, the annual fuel yield on gallons per acre. And then on this column is what is the gallons of oil per acre equivalent, because the energy content in the biofuel is less than in the oil. So this would be the productivity of how many gallons of oil equivalent are being produced. And then over here, final column is the area that you would require to produce 1 CMO of oil. These are all into thousands of square kilometers. And if you look at the smallest numbers over here are here for algae. And even then, it's lots of houses, 154,000 square kilometers for 1 CMO. So it's a lot. And of course, on top of that, it requires about roughly 5,000 gallons of water for every gallon of fuel. Not in the case of algae. If it's grown in the sea is how you're doing it, then you're not using the fresh water, but in many other cases you're using fresh water. So how do you, the way out is to see if you can improve the yields. And there are advances that I'm looking at these days in biotechnology, both in terms of microbiology and gene editing. CRISPR just wasn't around for a few years ago, but now with that you're able to go in and edit the genetic sequence so that the algae will produce the right kinds of the esters that you want, the right kinds of lipids, and be able to get a higher yield of your biodiesel. So cut down this 154,000 square kilometers, maybe by another factor of 3 or so. So to conclude, well, biomass availability is relatively small. When you look at the total global energy demand, it's already 4, it's growing maybe 6, and the maximum that we could get is about half a CMO. Nevertheless, bioenergy can be an important player. A sustainably grown biomass resource can provide storable green fuels, maybe for aviation, because that's one place where you cannot use batteries or you cannot use electricity to fly planes, and so maybe this could be used to produce jet fuel. You could augment the fuel used in waste incinerators. That's another way to also manage municipal waste. It would be an economic alternative to open field burning of crop residues to reduce pollution, as well as produce soil remediation for the farmers. And I'm looking at some advances in microbiology to improve the yields, both also I didn't mention earlier, consortia farming. That's, algae growing requires also some nitrogen input because algae don't fix nitrogen. But if you have cyanobacteria that are fixing nitrogen in conjunction with the algae, then the two can be worked in as a consortium. They could work together, and that would reduce the need for energy-intensive nitrogen fertilizers. So I think my time is almost up, and I thank you very much for your attention. And if people are interested, you should, my book I've showed here, it's a cubic mile of oil, to summarize in 3 little bullets what's in the book. Don't waste, be informed, and please talk to your people. I wish, really the challenge can be solved only with the public embracing nuclear power. Yeah, that's how the more I worked in it, the more I believe it. So hopefully one of these days the World Bank will begin to realize that, and they will start supporting. It's really a tragedy that they don't fund any of the projects in the developing world where is the greatest energy need is there, need for these clean energy sources. I thank you for your attention. I'll take some questions if there are any. Spandana, I pass it over to you.
All right. Thank you for the presentation, Dr. Malhotra.
Yeah, sorry. Back to the chair. Sorry. Yes.
All right. So I'll ask the audience if anyone has a question for Dr. Malhotra.
Thank you, Malhotra.
Thank you.
Sudhakar, thanks for attending the.
Yeah, can I ask a question?
I think you're
Dr.
muted.
Malhotra, can I have a question to you?
Sure, sure, sure.
Oh, I am Vasunendu Model from India.
Mm-hmm.
It's a nice presentation. In the morning, you have given a very interesting topic, that is bioenergy, which will definitely even go in a more space throughout the world. My question is, you have covered many aspects like the space requirements, the people involvements, the other aspects like economic front and all those things. But only one thing I would like to listen more from you. Is there any technological development happening to that extent in comparison in other energy sector we are finding? Because in the bioenergy, what we see since inception, the procedural aspect, the all activities involved in that are more or less similar. There are not much technological breakthrough to make it even more comfortable, more popular, and more obviously more and more economical results oriented. So what is your say in that? Is it going in a really satisfactory way, or you feel like it can be further improved?
Well, certainly there's plenty of room for improvement. There's no doubt about it. The land requirements are so large. If we can improve the yields of it, and if we can reduce the energy inputs or any kind of input that we have to make to harvest the crops, their benefit. And I mentioned a couple of them. One is the use of cyanobacteria along with the algae is a wonderful combination. I'm looking at that development. The second thing is that I'm looking at is really the advancements with CRISPR technology and how which didn't exist, but now scientists are going back into editing the specific genes, making the lipids in the algae and editing them right there so that the lipid profile is the one that is best suited to make jet fuel, that it really improves the process. Now, these are still very early studies, and it's a very long ways before you can really look at filling out a jet fuel, a plane with a tank full of algae oil to run, by these methods. They have done some demonstration flights with the regular algae oil, yes, but it's that's not the way to do it. It's not cost effective, and I don't see a way that for bioenergy to really address the global energy need. There are other non-bioenergy ways as well I can talk about where it makes sense to have carbon neutral, because our thing is the amount of energy and carbon reduction. These are the two things. Now, one aspect that I did not touch today at all is the use of bioenergy in conjunction with carbon capture and sequestration. So when you do that, you can get into the negative carbon. So that becomes a way of negative carbon. But the other way of doing negative carbon is also to to just pull it straight from the air, which gets very energy intensive. So using bioenergy to do that may be one way, but it will be added a small piece to it. I don't see it doing much more than that. But in terms of research, there are some very exciting research also in terms of thermophiles, high temperature bacteria that can do the processing, so you can have the pentoses as well as hexoses being converted, for that metabolism, for the conversion to ethanol. And so those are very exciting, and they are going on, but it's going to take some time.
Yeah.
We don't have any big processes. I've been hearing about them for many years, but they're still there. They're working on it.
No, it's fine. I mean, the technology is what you are talking about for increasing the production, for reducing the emissions. All are really happening. It's not that it's not happening. But my
no, it's happening. It's happening.
Yeah,
but
worry
can we wait? The question is, can the world wait?
No, another question is that can it be made little more sophisticated, compared to other energy technologies, definitely it is going to be very rural type of activities involved in bioenergy. It shows in that fashion. More and more education, more and more sophistications are not getting involved in the development of bioenergy, because this particular energy has started long before, and now we are trying to increase the production. We are trying to reduce its environmental aspects and all those things. I do not deny that. But my question is, can it be made a more sophisticated fashion so that the world is, how where they are going, the new generations what they're looking for. So how can it be made attractive to them also, having all the positive aspects that you are talking about? I'm just worried from that perspective. So if you feel like it is really required, then definitely you are the main person whom we should encourage to get it.
Maybe we can, I'll be happy to write to you about it. Maybe we can carry on the conversation. I know that the time is also moving on. And
yeah, that's right.
Chairman is probably looking at another. But yes, I just don't see how you can, why do you want to make it sophisticated? So you will have to explain to me. Please write to me. You have my emails over there. You can write, if you get it from them. It's just ripu.cmo@gmail.com. And write to me about it, because just making it sophisticated doesn't matter. The thing is, we have
the new generation children.
So for that, look at CRISPR is a very sophisticated technology. It's absolutely cutting edge. Being able to go inside and edit the very gene, etc., it's fantastic. Making new enzymes to do that, it's fantastic. So that's another. But ultimately, you will need, because you're relying on the sun, there's only so many joules that are falling on the planet Earth, and that's where you have to harvest it from.
Okay, thanks. Okay. Thanks for considering the question.
All right.
Thank you. Yeah.
Thank you.
Any last question from the audience?
Hi, Dr. Merrill, can you hear me?
Yeah, I can hear you.
Yeah, thanks for your presentation. I just have a question that you mentioned that for the conversion of biomass, there are gasification, combustion, and pyrolysis. So for these three technology, which one is better or is a better choice for the bio-oil production, for gasification or pyrolysis?
So it really depends on the situation, where you are, and what are the other benefits that you're looking for. Because if it's the only question is to produce energy, then combustion, obviously. But if you want to produce, if you don't, and do you have enough resource available to you to have a nice big plant? Because if collecting the biomass itself is going to be a larger hassle for you, then that's a consideration. So it really depends on where you are, which situation you're looking at. So the reason I mentioned pyrolysis and biochar is that the pyrolysis oil could run the machine that you are running to do the pyrolysis. You can use that its own stuff and produce the thing, and then you are not transporting the fuel. You are taking the fuel right from the farm and just returning to the farmer the biochar to augment his fields, and then move on to the next farm and go and do that. Whether it works or not is a difficult thing. I cannot answer that. I haven't done the full analysis, and I would like to do that maybe in conjunction with some farmers to see what their needs are. And again, it depends.
Okay,
too many variables. Too many variables.
And another just that, is there any commercial application for the pyrolysis in USA? We know that for gasification or combustion is just can be used for large scale, but for pyrolysis, is there any demonstration plant or commercial plant for biomass?
So there are small demonstration ones that are there, or pilot ones I have seen for pyrolysis, bio-oil. But bio-oil is not very useful useful oil. It's a bio oil has got very poor quality. The best thing you can do is to just burn it right away and kind of for running your own machine. That's about it. If you want to convert it into transport the oil into for a refinery, it can be done. But then you have to have another unit next to your pyrolyzer that upgrades it, deoxygenates it, dewaters it sufficiently so you can make it into a feedstock for the refinery. So that just increases another level of sophistication, and then it becomes, well, do I do that with the forestry waste, or do I do it with the farm waste? And that's a consideration. Forestry waste, I mean, in California, we are looking at it very seriously because we have these annual big forest fires. That's really, so extending, being able to use the forest residues at the bottom, you know, the undergrowth that they talk about, if there's a way to harvest that undergrowth so that you reduce the danger of the fires, and you can have you improve the life of your forests, and forests are a valuable resource.
Okay.
So
thank
that's
you.
the other benefit. But in terms of just the energy cost, hello. Okay.
Some network.
There's some echo here.
Okay. Okay. Thank you.
Thank you.
All right. So thank you, Dr. Malhotra, for the presentation. I think if the audience have further questions, I'm sure